Hello, this is Miss Moore, and today during chemistry we're going to be discussing stoichiometry, specifically mole-mole conversions. Today's essential question: given the number of moles of reactant used, how do you calculate the number of moles of product? Please remember you need to completely answer this question in your summary. For today's lecture, you will need handy your calculator and your periodic tables. Oh, and your unit conversion tables as well. Stoichiometry is really all about math, which means we need to talk once again about significant figures. So we'll start with a real quick review of significant figures. So first thing we need to know about significant figures is that every non-zero digit is significant. So if I had a number like 2162, there are 4 sig figs there. If I had a number like 8.691, there are again 4 sig figs. Okay, so every non-zero digit is significant. All right, how about zeros? Well, zeros between non-zero digits are significant. So if I had 5002, those 2 zeros are significant, as well as the non-zero digits, so we have 4 sig figs. If I had a number like 1020004, this 0 is between 2 non-zero digits, as are those 3. So it looks like we have 7 sig figs. All right, and then zeros before and after a decimal are significant as long as there is a non-zero digit somewhere before the 0. Okay, so if we had 200.00, all of these zeros are significant because the first 2 are before a decimal, the second 2 are after a decimal, and there is a non-zero digit in front of it. So that gives us 5 sig figs. Okay. If we had, let's see, 0.00100, okay, this time there are only 3 sig figs. Okay. These are not significant. While this one is before a decimal and these 2 are after a decimal, there is no non-zero digit before them, so they can't be significant. A calculated answer cannot be more precise than the least precise measurement. Okay, that means the number of sig figs needs to equal the least number of sig figs in your problem. Okay? And so the answer should be rounded to the same number of sig figs as a measurement with the least number of sig figs. All right, and that's it for our review on sig figs. All right, next we're going to do a quick review on chemical reactions. Stoichiometry is mathematical calculations using balanced chemical equations. So we need to remember what a chemical reaction and a chemical equation is. So a chemical reaction involves changing substances. In a reaction, one or more substances known as the reactants, the things you start with, change into one or more new substances known as the products, the things you end up with. Equations describe a system that rearranges atoms and bonds to make new substances. So a reaction is what occurs in your reaction dish, in your body, in the world. An equation is what you write down on the piece of paper. Stoichiometry is a method of chemistry that uses balanced equations to predict a couple things. It's used to predict the exact amount of product produced from a certain amount of reactants, the exact amount of reactants needed to produce a certain amount of products, the truth is you could also use it to, if you know the amount of one type of reactant, you can predict how much you need of the other type of reactant, whatever. Okay, so stoichiometry uses mathematical calculations to predict how much product or reactant is needed or produced. Okay, before we get into how to do mole-mole conversions, I want to go over a few terms or give you a few things that are going to be necessary for this unit. Okay, first is the stoichiometry map, okay, which is mass known goes to mole known, goes to mole unknown, goes to mass unknown. This map is extremely useful. A lot of people don't like using it, but it is extremely useful. So if you guys could copy down that map really quickly in your notes. And then the conversion factors we're going to be using this unit. There's a whole bunch of them. We've got mole-mole ratio, which is mole known to equals mole unknown. We've also got 1 mole known equals the molar mass of known in grams, and 1 mole unknown equals the molar mass of unknown in grams. These you can copy down in your notes. You can also put these conversion factors in your unit conversion table. Okay. The factors. The map cannot go in your unit conversion table, okay? No unit conversion table, but the conversion factors can. So take a moment to copy those down before we proceed. All right, it's time to get started on mole-mole conversions. So the first thing we need to talk about is coefficients in a balanced equation. Coefficients are actually showing you the number of moles of each molecule or element being used or created in a reaction. So we have a reaction here. We have C6H12O6 plus 6 O2s produces 6 CO2s and 6 H2Os. What this is really saying is that we have 1 mole of the C6H12O6 because there's no coefficient there. We have 6 moles of oxygen. We have 6 moles of CO2, and we have 6 moles of H2O. Okay, so the coefficients actually are showing us the number of moles of each molecule or atom in the balanced equation, or used in the reaction. Okay, so now that we know that these are moles, the coefficients, we can actually use these to make something called mole ratios. Okay, so a mole ratio is like saying 1 mole of C6H12O6 equals 6 mole of CO2, which is a true statement. For every 1 mole of C6H12O6 we use, we're going to make 6 moles of CO2. Okay, we could do that again with, we could have 6 mole CO2 equals 6 mole H2O. That's also a true statement because for every 6 moles of CO2 we produce, we also produce 6 mole of H2O. So a mole ratio is really just putting the number of moles of an atom equaling, or molecule, equaling the number of moles or molecule of another molar molecule in the equation, in the reaction. And we're going to be using these mole ratios as an equality, which we talked about back here. Mole ratio, which is mole known equals mole unknown. Okay, so when doing mole-mole conversions, these mole ratios are going to be our conversion factors. Remember the conversion factor, like 1 foot equals 12 inches? Well, this conversion factor could be something like 1 mole C6H12O6 equals 6 moles O2. Okay, so mole ratios can be used like conversion factors to compare amounts of substances. So when we're doing mole-mole conversions, you're going to find the coefficient in moles, use the unit moles, for the 2 atoms or molecules in the question. And where do you find this information? Well, from the balanced chemical equation. Right? The balanced is where you get the coefficients. Okay, so that's where that information comes from. After you do that, we're going to use a 3-step conversion factor method, just like we've done in the past. Okay, we're finally here. We are now going to talk about the steps for completing mole-mole stoichiometry conversions. And our example, as we're going through the steps, will be how many moles of CO2 would be created from 3 mole C6H12O6. And, of course, we need to have a balanced equation. So that's the balanced equation. C6H12O6 plus 6O2, or 6 moles O2, produces 6 moles CO2 and 6 moles of water. All right, so step 1 is to rewrite the problem as a math problem and then set up the map. So let's do our math problem. How many moles? That would be our x, and what we know is 3 moles C6H12O6. So we'll have 3 mole C6H12O6 equals x mole CO2. Okay, so we've figured out our math problem. The next thing to do is to set up the map. Understanding the map isn't completely important for today. However, as we get to more and more complicated stoichiometry problems, it becomes more and more important to know how to use the map. So in my opinion, we should learn how to use it when we're on easier problems. Okay, so what we do, the known, we'll start with the known. Known, that's something we know something about. For example, we know 3 mole of C6H12O6. Unknown, on the other hand, is going to be our x, our question, right? X mole CO2. So let's see, a map, hopefully you guys know how to use a map. A map is a way to find out how to get to where you're trying to go. You know where you're at, you know you want to end up, and the map gives you directions for getting there. So if we start with the known, what do we know about the known? Do we know the mass, or do we know the mole? Well, it says 3 mole. So what we know is the mole. We know we have 3 mole C6H12O6. Okay, so we're done with the known part. The unknown, the x, what do we know? Do we know mole or do we know mass? Well, we know mole. We're trying to find mole, I guess is another way to put it. We don't know the mole of CO2. So that's our map. We know where we're starting at mole, and we know where we're finishing at mole. All right, so the next step is to set up the grid and write the given, the known from step 1 over 1, right? So our known is 3 mole C6H12O6 over 1. Okay, next up we've got to insert our conversion factor or equality. So you're going to determine the mole-mole ratio from the reactants and products you're interested in. So the mole-mole ratio is your equality, the coefficients from the balanced equation. Okay, so that's what we're going to look for. So let's go back and look at our balanced equation. Okay, and so if we look at our math problem, we're interested in C6H12O6 and CO2. Okay, so up here we have C6H12O6 and we have CO2. So our equality is going to be 1 mole C6H12O6 equals 6 mole CO2. And I picked which molecules I was interested in from the math problem, right? And I picked 1 mole for C6H12O6 because there's no coefficient there. That means 1. And I picked the number 6 mole for CO2 because 6 mole. All right, so we have our mole-mole ratio that we got from the balanced equation. So now we need to take this conversion factor and put it in the grid, setting it up so all units cancel out. So let's look. Oh, we have units mole here. So which one goes on the bottom? Mole and mole, they're both mole. So how do we tell? Well, what is different? We have different molecules, right? So this time we're going to identify which molecule by matching. So since we have 3 moles C6H12O6 on the top, we're going to put mole of C6H12O6 on the bottom and 6 mole CO2 on the top. Okay, let's make sure we set this up right. Stupid mistake blocker. Does mole C6H12O6 actually cancel out mole C6H12O6? It does. So now all we have to do is the mathematical calculations. So we multiply across the top, we multiply across the bottom, and then we divide. So when I multiply across the top, I came up with 18 mole CO2 over 1. That's how you do the calculations. Now, however, we got to go back and look at sig figs. We've got 1 and we've got 1. Our answer, however, has 2 sig figs. So we need to only have 1 sig fig. So we look at the first number we're going to drop, which is an 8. That bumps the 1 up to a 2. So we're going to have 2 mole CO2, which doesn't really work, right? Because 2 is nothing like 18. But remember, when you're dropping or rounding a number before a decimal, you need to put a placeholder. So we can have 20 mole CO2. We could also, if we're more comfortable, put 2 times 10 to the 1 mole CO2. Okay, so that, ladies and gentlemen, is how you do mole-mole conversions. It is now time for a practice problem. If you think you can do it on your own, why don't you hit pause and try to do it on your own? If you don't feel like you can do it yet, go through the steps with me, and then you can hit pause and try the next one. All right, so the first thing we need to do is figure out the math problem, which is 22.34 mole Al equals X mole O2. Okay, and then let's figure out our map. So our known is Al, right? We know Al. What we know about Al is that we have 22.34 moles of it. Okay, what we're trying to figure out is the unknown, which happens to be O2, and what we're looking for is mole O2. All right, next we need to set up our grid and put in the grid our known, which is 22.34 mole Al over 1. All right, next we need to find our equality, which is the mole-mole ratio from the balanced equation. So our known, what we know about is Al. What we're looking for is O2. So our mole-mole ratio is going to be 4 mole Al equals 3 mole O2. All right, who are we going to put on the bottom? Well, we have mole Al on the top, so we're going to need to use mole Al at the bottom. So we have 4 mole Al at the bottom, 3 mole O2 at the top. Let's cross out, stupid mistake blocker, mole Al, mole Al. A good thing to do now is look, I'm at mole O2. Is that where I wanted to be? It is. Okay, so next let's multiply across the top. And that gave me 67.02 mole O2 over 4. And when we divide, yeah, 16.755 mole O2. All right, let's go back and look at sig figs. We have 4. We don't use the moles from the balance equation in our sig fig calculations. We only use our given. So we have 4 sig figs, which is these 4. And the one we're going to drop is 5 or bigger, so we're going to end up with 16.76 mole O2. All right, and that is our final answer. Okay, why don't you try the next problem on your own? All right, this time I was a little mean. I didn't give you the balanced equation. You are going to have to write the equation by yourself. All right, so how do we do this? Well, we know that tin reacts with hydrogen fluoride. So we should ask ourselves some questions before we go on. First of all, single atom, is he diatomic? He is not, so we're good there. This one here, ionic or covalent? It's ionic, so we need to check charges. And H has a 1 plus, F is a 1 minus, so we're actually neutral, so we're okay there. Okay, and that produces tin 2, SN, 2 means 2 plus, fluoride, which is a 1 minus, check charges and neutralize, so we end up with SNF2 plus hydrogen gas. We have to ask ourselves, diatomic? The answer is yes. And then from there, we need to balance it. And to balance this one, it's pretty simple. If we put a 2 there, we're all balanced. All right. Now, if you hadn't hit pause yet, please hit pause and try to do this by yourself. All right, so now we need to write our math problem. And our math problem will be, we have 33.4 mole of hydrogen fluoride, and we're trying to figure out the number of moles of tin fluoride. Okay, the next thing we need to do is fill out our map. We have our known, since we know something about it, is, what is it? It is mole of HF. So that's going to go in the known area. 33.4 mole HF. And our unknown is mole again, blank mole, SNF2. Okay, that being said, I'll get rid of this to make a little bit more room. Okay, so now we need to set up our grid and put our known in there, which is 33.4 mole. Oops, I forgot to write HF. 33.4 mole HF over 1. All right, so now we got to figure out our conversion factor, which is going to be our mole known and our from the balanced equation, and that would be the HF. So we're interested in the HF from the balanced equation. And our unknown is the SNF2. And we find that in the balanced equation. So our equality will be 2 mole HF equals 1 mole SNF2. All right, so who's going to go on the bottom? Mole HF. So 2 mole HF goes on the bottom, and 1 mole SnF2 goes on the top. All right, let's do our stupid mistake blocker. Mole HF cancels out mole HF. When we multiply across the top, we get 33.4 mole SnF2 over 2. And when we divide, we get 16.7 mole SnF2. All right, our number of sig figs should be 3, which it is. We're done. That's it for today. Have a good one, folks.